okay? So we introduced this idea. So we had one relationship that we've been talking about for a while, which is if you've got a vector space, a subset of that vector space might be a subspace if it is a subspace, meaning it's a vector space in its own right, if it's closed under addition and scalar multiplication, right? So we had this one relationship between two vector spaces where in that one of the spaces could be a subspace of the other. But then we introduced this sort of extra way of relating spaces by talking about the sum of two spaces. So now we've got some big vector space and two subspaces sitting in that space. And we're introducing another vector space, which is this thing v plus w, which is a set of all things that you can make by taking something from v and something from w and adding them together. Right? So we call that the sum of the two spaces v and w. And we say that sum is direct if v and w don't share anything except the 0, and they've got to share the 0 because they're both subspaces. Okay, so a little application of the subspace test proves that this thing is in fact a subspace, so that's on the problem set, so I won't go over that. But what I want to explain now, and I sort of mentioned this but didn't prove it before the break, which is really the motivation for looking at direct sums rather than just sums of vector spaces. The nice thing about a direct sum of two vector spaces is that there's a unique way of writing everybody in the sum as something from the first space plus something from the second space, right? If the sum's not direct, then there's going to be infinitely many ways of decomposing a vector in the sum in general. But if the sum is direct, there's a unique way of decomposing any element of the sum. Okay, so the proof here, I think, is quite cute. It's not intuitive, but it's a nice trick, and it's a nice trick that works quite often. So it's good to see this. This is sort of, you know, your lucky day. You get to see this trick for the first time in your life, probably, and you'll probably want to use it again sometime. And we certainly will use it again in this unit. So let's see how we do this, right? So let's suppose that v plus w is direct, right? And so what we mean by that is that the intersection of v and w is the 0 vector. Okay, now let's suppose that this is, I guess this part of the strategy is kind of familiar. We're trying to prove uniqueness, so what do? We assume that we've got two versions of the thing we're trying to prove are unique, and then we show that they actually have to be the same thing, right? So let's suppose we've got some u, and we've got, well, we do have some u and v plus w. Let's suppose we've got two different ways of writing or decomposing u as something from v plus something from w. So we're trying to prove uniqueness, and we're going to sort of start off by assuming non-uniqueness, but then show that in fact these potentially two different ways of writing u have to be the same, right? So we're assuming that u is v plus w, but it's also v prime plus w prime, where v and v prime live in v, and w and w prime live in w. Okay? Now, if I was just to stare at this equation, what would I want to do? Well, one thing I can do is convince myself that that holds, right? So this assumption is the same as that. I just take v prime over to the left and w over to the right. Now, let's think about where does this guy live? Where does v minus v prime live? V, right? Why?
Based on what we defined above.
So V and V prime live in V, so their difference lives in V because V is a vector space, all right? So V is a subspace, so it's got to be closed, so this thing has to live in V. And where's W prime minus W live? Lives in W. Okay? So this is since V and W are subspaces, V minus V prime lives in V, and W prime minus W lives in W. But this also means, right, because V minus V prime is equal to W minus W prime, it means that V minus V prime lives in W. Right? Because this thing lives in W, and V minus V prime is equal to that, so V minus V prime is going to live in W as well. So this thing actually lives in V and W. And similarly, this guy lives in W, but it's equal to this guy that lives in V, so it has to live in V. So the right-hand side lives in V and in W. So V minus V prime lives in V and W. W prime minus W lives in V and W. And what's the only thing that lives in V and W? 0. That's the key observation, right? We can tell that this thing, we rub some scroll out, we can tell this thing is 0 because it lives in V and W. And therefore V equals V prime. And we can tell this thing is 0 because it lives in V and W, and therefore it's equal to 0, and W prime equals W. Okay? So we have uniqueness just by knowing which spaces these guys live in, and the assumption that the spaces only intersect at 0. Okay, so let's write that down. So V minus V prime equals W prime minus W tells us that V minus V prime is in W, and analogously W prime minus W lives in V. So V minus V prime and W prime minus W live in the intersection, but that's 0. So V minus V prime equals 0. This tells us that V equals V prime. And W prime equals W. Well, it equals 0, so W prime equals W. Okay? So that's only proving one direction, but it's kind of, I guess, the interesting direction. I'll leave the other direction as an exercise on the problem set. But what we've shown is that if the sum is direct, then you have uniqueness. So I'll leave it to you to prove that if you have uniqueness, the sum has to be direct. Okay, so the converse is on the problem set. All right, does that argument make sense? Everybody happy? All right. So what else can we figure out about these spaces? So this definition about the sum and about direct sums is completely general, right? This works for arbitrary abstract vector spaces. You can write down these constructions and they make sense. But then the last thing that we did before the break was say, well, let's go back and picture Euclidean n space for a second. Because in Euclidean n space, we have this extra bit of structure called the dot product. And if you have a dot product, then you know what it means for two vectors to be orthogonal. And we introduced this idea of two vector spaces being orthogonal, right? So we say W is orthogonal to V, or V is orthogonal to W. It's symmetric. If everybody in V is orthogonal to everybody in W. Okay, so you take any element of V and you compute its dot product with any element of W, you get 0. Right? Then we say W and V are orthogonal. So everything in W is pointing in completely opposite direction to V. So in particular, here's an example. If you're in R2, if you take the x-axis and you take the y-axis, they're orthogonal. Right? Because everything on the y-axis is orthogonal to everything on the x-axis. Just as an example. That's R2. All right. So the reason this is related to what we were just talking about is that if two spaces are orthogonal, so two subspaces of Euclidean n space, if they're orthogonal, then their intersection is 0. And this is not a hard thing to prove. So let's take something in V. If you got U in V, then it's orthogonal to everything in W, because we're assuming V and W are orthogonal. Okay, that's just the definition of what it means for V and W to be orthogonal. But that means that if you take something that's in the intersection, it means U's got to be orthogonal to itself, right? Because then U lives in W. By assumption here, U has to be orthogonal to everything in the space W. If U happens to live in V and W, it's got to be orthogonal to itself. And we know that the only thing that's orthogonal to itself is the 0 vector. Okay? So that tells us that U has to be the 0 vector, and therefore the only thing in this intersection is the 0 vector. Okay, so let's write that down. So if U lives in the intersection, then it has to be orthogonal to itself, right? Because it's got to be orthogonal to everything in W. It lives in V, it's got to be orthogonal to everything in W. It also lives in W, so it's got to be orthogonal to itself. The only thing orthogonal to itself is the 0 vector. And so we've shown that if you look at any arbitrary element of the intersection of these two orthogonal spaces, that element has to actually just be the 0 vector. So that tells us that the intersection is just the 0 vector, right? Because we started by assuming nothing about U except that it lived in the intersection of these two orthogonal spaces. You immediately conclude it has to be the 0 vector. Okay, so why is that useful and interesting? It means that the direct sum of any two orthogonal spaces, the sum of any two orthogonal spaces is a direct sum. Okay, so if you're sitting in Euclidean n space, which is where we're going to want to sit if we're talking about these matrix spaces that we're talking about before the break, the row space, the null space, etc. If you're sitting in Euclidean n space and you've got two orthogonal subspaces, their sum is immediately a direct sum. So this is a sort of a quick and easy way of proving that a sum is a direct sum. Okay, so that's what this corollary says. If your two spaces are orthogonal, their sum is a direct sum. That's what that's an immediate consequence of what we just proved. Okay. Is everybody happy with that? So we've got direct sum. The nice thing about direct sums was you have unique decompositions of everything in that sum into something from the first space plus something from the second space. That has nothing to do with inner products. The next observation was that if you sit in a in a space where we have an inner product, a dot product, which so far for us is just Euclidean n space, but we'll generalize it later. But so far it's just Euclidean n space. If you have two orthogonal spaces, their sum has to be direct. Okay. So the last new ingredient that I want to talk about, and we talked about this briefly before the break, is the idea of an orthogonal complement of a subspace. And let's stick in Euclidean n space so we know what orthogonal means for the time being. So the orthogonal complement of W is this set that we call W perp of all the vectors in Rn, the big space that W is a subspace of, all the vectors in Rn that are orthogonal to everything in W, right? So W perp is a set of all things in Rn that are orthogonal to everything in W. And the first claim is that W perp is a subspace. So we can prove that. That's just the subspace test again. So what do we need to do to prove, well, to apply the subspace test? We show that the space we're interested in is not empty, then we show that it's closed under addition and scalar multiplication. Okay. So what's one thing that has to be in W perp? 0, right? Because no matter what W is, 0 is going to be orthogonal to everything in W, right? Because 0 is orthogonal to everything. You take any vector and you dot it, any vector in Rn, Euclidean n space, you dot it with the 0 vector, you get 0. Okay? So 0 definitely lives in W perp, right? Because 0 dot W equals 0 for not just for every W in W, but for every vector in Rn. But certainly for every W in W, that holds. And that tells us that 0 lives in W perp. And so in particular, W perp isn't the empty set because it's got something in it. So now we can talk about closure. So now let's take two things in W perp. Now, we want to show that the sum of these two vectors in W perp is also in W perp. So how are we going to do that? What do we need to show?
To do it sum 0. You do it, it's only 0.
That it's only 0?
That means it's
When they add together and dot with some arbitrary vector with W that is equal to 0, then that means it's perpendicular.
That's what we've got to show, right? We've got to show that the sum satisfies the defining property that W perp satisfies, right? And the defining property of W perp is that it's a set of everything that's orthogonal to everything in W. So what we've got to do is take an arbitrary element of W and consider what its dot product is with V1 plus V2. So V1 plus V2 dotted with W. We know how to simplify this because we're just back in first year land where we're taking dot products of things in Rn. So I can expand that out. And this is 0 because V1 lives in W perp. And this is 0 because V2 lives in W perp. This is 0 plus 0, which is 0. And what that tells us, right, and that holds in particular, right, that holds for every W in W, because all I assumed here was that W is in W and V1 and V2 are in V. That's all I used to show that the dot product of the sum with W was 0. So that holds for every W, and that means that V1 plus V2 is something else that's orthogonal to everybody in W. Right? So the sum lives in W perp as well. So W perp is closed under addition. Now, take some scalar. You play the same game. we want to show that kv1 lives in W perp for any scalar. So what does that mean? It means you've got to take kv1 and you've got to show that if you dot it with anything in W, you get 0. But again, we know how to simplify this. That scalar just comes out the front. I've got v1 dotted with W. That's k times W. Sorry, that's k times 0, which is 0. That holds for all elements of our space W. So kv1 is orthogonal to everything in W because it's dot product with anything in W with 0. So kv1 lives in W perp, right? Because it's one more thing that is orthogonal to everybody in W. Okay? So W perp is closed under addition and scalar multiplication. So W perp is a subspace. And a subspace of what? A subspace of Rn, because that's the space that we're talking about subsets of. Okay, does that make sense? Question?
Yeah, so when you say that like anything in W, like that W vector we're writing out for like these two, like for the addition and scalar multiplication, that literally just any W.
Absolutely any W in the big space W.
So, and then, so everything in W perp, like anything in W perp would be orthogonal to it? Like,
Yes, right? So here's, I know that's not a very good diagram, but that encodes everything, right? So what I mean when I say this is an R2. So let's say this is W. So W is the y-axis. Then you think about what's W perp. It's the x-axis. Because anything along here, take some vector along there, and you ask the question, what's the biggest set? What's the set of all things that's orthogonal to that vector, right?
Yeah.
So anything along this axis, any one of these points along this axis, no matter how long it is, whether it points this way or whether it points that way, it's orthogonal to that guy,
yeah.
right? And it's also orthogonal to that guy. Any of these guys is orthogonal to that guy, or that guy. Okay, so that's the simplest concrete example of this.
Yeah, okay.
Yep.
This might be a bit weird, but I'm wondering, is this tied to linear transformations? Like, you have a graph and you can use like cos or sine to like turn like into orthogonal or not? Is that a possible manipulation we're going to see in the future?
Of orthogonal transformations. We're going to see these subspaces turn up actually as a way of understanding all transformations. So that's probably the least cryptic answer I can give at this point. There's probably nothing terribly special about the orthogonality of it, but it's definitely a way of understanding what's going on when you transform things. Okay. All right, so is everybody, why did I put that there? That was all set to go. All right, is everybody happy with that? All right. So, now we move on to something actually quite deep. So the point of this orthogonal perp stuff, this orthogonal complement stuff, is that if you take any subspace of Euclidean n space, then you can decompose Euclidean n space as the direct sum, right? Direct sum of W and its orthogonal complement, okay? No matter what W is. Now it has to be a direct sum here, not just a sum, because W and W perp by construction are orthogonal to each other, right? So we know that the sum has to be direct. What's interesting is that you can make everything in Rn, because the sum's direct, you can make everything in Rn by taking something from W and adding something from W perp. And there's only one way of doing that. No. It's not going to be just 0 because that's the direct sum, not the intersection. The intersection would be 0 for sure. Right? But we're talking about, this is all the things you can make by taking something from W and something from W perp. So you'll get some big collection of vectors in Rn. What this theorem is saying is actually it's all of the vectors in Rn. There's nothing left over. You get everything. You can make all of Rn by taking something from here plus something from there. Yeah?
Sorry, just with regards to the notation.
Yep.
Since the direct sum is sort of like a subset of a regular sum, is it still okay to use the regular plus symbol, or would that be considered incorrect here?
It's not incorrect, right? No, that's correct. It's just less informative. Yeah. Yeah. I wouldn't write it in an exam because it would suggest to me that you don't know it's a direct sum. Right? So, but it's not incorrect. It's just less informative. Okay, so we're not going to prove this here. We will prove it though, but we can prove a much more general version of this, right? So what we're going to do is, instead of proving this for Euclidean n space, I'm going to, in a couple of weeks' time, tell you how to generalize what a dot product means into an abstract vector space, which is a thing called an inner product. And then there's a version of this that works for any inner product space, not just Rn with the dot product. So we'll prove it there when we've got a little bit more machinery. So for the time being, so we'll come back and I'll prove it in full generality without any kind of circular reasoning. But I don't want to do it yet because we need abstract inner products. But I'm stating it here now because I want to go back and use this to understand this row space, null space stuff. All right? Okay. So all I need at this point is that you sort of understand what this statement means, not how to prove it yet.
I guess we can use like R2 to picture it.
What's that?
We can use R2 to picture it.
Yes, so you can use R2 to picture it.
Right, yeah.
Yep. If you just picture the x and y axis, you get what's going on. Right? Everything in this theorem is just higher dimensional versions of that. All right, let's do a poll. All right, here's a poll trying to get your head around this idea. All right, so let's say that U is the xy plane, V is the xz plane, and W is the y-axis. So now we're in R3 instead of R2, just to make it a little bit more interesting. So which of the following statements are true? R3 is the direct sum of U and V. R3 is the direct sum of V and W. R3 is the direct sum of W and U, or all of the above. So I think it's a really good idea to write down sort of concretely what U and V and W are to help you think about it. So U, if you think about it, is, right, it's, what is it? It's the, what do we say, the xy plane. So it's the span of E1 and E2. Right, that's what we mean by the xy plane. And V is, what do we say, the xz plane? So it's the span of E1 and E3. Right, and there's nothing special about calling the coefficients V1 and V3 here. I'm just doing that to try and be intuitive. You can call them X and Y or X and Z or whatever you want to call them. Or a picture of a dog and a picture of a cat, really doesn't matter. And W is the y-axis, so it's the span of E2. All right, that's what U and V and W look like. So there's two statements here I guess you need to think about. Firstly, is R3 actually equal to the sum of these things? these two spaces, and then think about whether the spaces are, the sums are going to be direct or not, because the, you know, for instance, possibly the spaces are orthogonal. All right, let me check how people are going. Okay, we're doing reasonably well. So let's think about A. So, is R3 the direct sum of U and V, right? So this is U and V. So the first thing to observe is that you definitely can make everything in R3 by adding something from U plus something from V, right? So the sum of U and V is R3. But what's the intersection of U and V look like? Yeah, so there's a whole pile of vectors that lie in the intersection of U and V. And if we want the sum to be direct, we need the only thing in their intersection to be 0, and that's not the case here. So E1, for instance, lives in U and V, right? And E1 is not the 0 vector. So the intersection of U and V is not just the 0 vector. So U plus V, the sum, is not the direct sum of U and V. Right? In fact, this thing doesn't exist. Okay? So it's not A because the intersection of U and V is not just the 0 vector, so the sum of U and V is not direct. Okay, let's think about B. So that also rules out all of the above because A is false. Right? So let's think about B. So B says that, well, let's look at it again. So we're looking at V plus W. Now, if you add something from V plus something from W, you definitely can get anything in R3, right? Because what you'll have is some multiple of E1 and some multiple of E2 and some multiple of E3. So you can generate all of R3. And also, you'll notice that these spaces are orthogonal to each other, right? If you take any multiple of E2 and dot it with some linear combination of E1 and E3, you get 0, right? So V and W are orthogonal, and in particular, the only thing in their intersection is 0, and therefore their sum is direct. And what does their sum look like? Their sum is anything of the form something E1 plus something E3 plus something E2. Doesn't matter what I call these coefficients. They're just any real numbers. So that's R3. Okay, so in particular, in this case, this doesn't have to be true in general, but in this case, W is actually V perp, right? So from our previous theorem, we knew that their direct sum should be R3. So it is B. And you can see that the problem with C, what are we looking at? The problem with C is what?
There's two.
There's two problems.
That's the V. There's two E2s.
There's two E2s, which is the same problem as A. There's also no E3s. So these two guys have a lot of overlap, and they don't generate R3, right? So the direct sum is definitely not all of R3. So their sum is not equal to their direct sum, and their sum's not even R3. So this was sort of wildly false. Okay. All right. Are you still happy? Okay, so that's really it for the abstract stuff. So now I want to get to the point of this in the current context. So are there any questions about all of this direct sum perp stuff before we move on? You got these concepts kind of clear? All right, so what I want to tell you now is the main observation. Okay, and there's sort of two things here, I guess a theorem and a corollary. So the main observation is that the perp of the row space is the null space. So that's how the null space and the row space are related to each other. Okay? So you remember the null space, you've got an m by n matrix. The null space is a subspace of Rn. The row space is a subspace of Rn. And we are saying, so we've got two subspaces sitting in Rn, and we're saying these two subspaces happen to be the orthogonal complements of each other. Okay? So that's a very precise way of describing how they're related. They're the orthogonal complements of each other. And what that means as a corollary, because of our previous theorem, right? Our previous theorem, just going back, was that Rn, you take any subspace of Euclidean n space, so for instance you take the row space, or you take the null space, Rn is the direct sum of that space and its orthogonal complement. So now that we know that the null space and the row space are perps of each other, we can write Rn as the direct sum of something from the row space plus something from the null space. And why is that interesting? Well, Rn is the domain of the matrix transformation corresponding to our matrix A, right? So what we've now done is decompose the domain of our transformation in a unique way into something from the row space plus something from the null space, right? Everything in the domain can be uniquely expressed as something from the row space plus something from the null space. That's what part A of this corollary tells us, right? Everything in the domain can be written uniquely as something from the row space plus something from the null space. And the two things in the row space and the null space are orthogonal to each other, right? Because everything in the row space is orthogonal to everything in the null space because of our theorem. And likewise, Rm is the direct sum of the column space and the co-kernel. So this is why the co-kernel enters into the picture, right? So far it might have seemed weird why we're interested in the null space of the transpose, but this is why. Because now we can decompose the codomain of our matrix transformation into the direct sum of the column space and the co-kernel. So everything in the co-kernel can be written uniquely as something from the column space plus something from the co-kernel. Okay? And we already know that the column space is actually the range of our matrix transformation, right? So what we've got is we've decomposed the codomain into the range plus something that's orthogonal to the range. All right. So let's think about the corollary first. Let's assume that we know the theorem. So 479, or was it 4710? I better check. 479. Oh, that's 4710. 479 tells us that Rn is the direct sum of the row space, because the row space is a subspace, the direct sum of the row space and the perp of the row space. But then the theorem tells us the perp of the row space is the null space. Okay? So that's easy. And then how do we get B? we get B by just applying part A to the transpose. So Rm, so by A, Rm is the row space of A transpose plus the null space of A transpose, right? Because A transpose is just a n by m matrix. You just apply part A. But the row space of A transpose is the column space of A, right? Because it's the row space of A transpose is the span of all the rows of A transpose, but the span of the rows of A transpose is the span of the columns of A. Okay? So if you've got the theorem and you've got, so we've got two ingredients here, the fact that the row space is the perp of the null space, and that our other more general theorem that Rm is always, always be written as the direct sum of any space and its perp. We get this very nice and useful decomposition of the domain and codomain of our matrix transformation. So all we've got to do now is prove that the row space is the perp of the null space. And it's actually not as complicated to do that as it might sound. Okay. So what we've got to do is take something in the row space and show that it lives in the null, that it's orthogonal to everything in the null space. Okay, and vice versa. All right. So so that we've got some language to actually make sense of all this, let's say that the rows of A are called R1 up to Rm. Right? It's an m by n matrix, so that has to be true for some collection of vectors. Right? So I'm picturing each of these Ri's as being a row vector of length n. Right? Because A is an m by n matrix. So let's say A looks like that. Now, we want to show that each of the rows is orthogonal to any element of the null space. That's going to be our starting point, right? Now, that's not quite enough. What we really want to show is that any element of the span of all the rows is orthogonal to any element of the null space. But once we know that all the rows are orthogonal to everything in the null space, we can just take linear combinations of those things and the rest will sort of come out. So let's start off by just considering what AX looks like, remembering our sort of favorite way of writing AX. Right, it's this linear combination of the columns of A with the coefficients coming from X, or just definition of matrix multiplication, if you like. Now, let's write these entries of A using the rows. Okay, so what's Aij? It's Ri, the jth entry. All right, if you think about it, if you go and search, if the ith row of A is Ri, and you go and pick out the ij entry of A, what are you doing? You're going down to the ith row, which is Ri, and then you're going along to the jth coordinate. So it's just the jth entry of Ri. So this is true just by definition of what these Ri's are. But now, what's that sum? What does that look like? What does it look like? What kind of object is it? So the first sum's matrix multiplication, right? That's matrix multiplication. But what does this one look like? It's the dot product of Ri and X. Right? It's the dot product of Ri and X. So I haven't assumed anything about where X lives yet. That's just true for every X. Right? The ith entry of AX is Ri dot X. You can take this as a little identity that you might want to use some other time. Now, what are we trying to show? We're trying to show what happens when X lives in the null space, because we want to show that all the rows are orthogonal to everything in the null space. So now let's assume that X does live in the null space. So if X lives in the null space, by definition, that means AX equals 0. But if AX equals 0, that means all of these numbers are 0, which means all of these dot products are 0. Okay, so any element of the null space is orthogonal to every row. Now, if you take an element of the row space, what does it look like? Well, it's some linear combination of these rows. So I don't know what these coefficients are, but there's some choice of the CIs such that R equals this sum here. But we know how to simplify dot products. If we want to be fancy, we can say the dot products act linearly. And we will explain things in fancy language like that in a few weeks' time. But for the time being, you know how to do this because you did it in first year. Each one of these is 0, so the whole sum's 0. Which means that any element of the row space is orthogonal to any element of the null space. And what that means is that, any element of the null space is orthogonal to any element of the row space. So this X, which lived in the null space, belongs to the perp of the row space, right? Because it's orthogonal to the row space, any element of the row space. So what we've shown is that the null space is a subset of the perp of the row space, right? Because we took an arbitrary thing in the null space and we showed it was orthogonal to everything in the row space. If we want to show that these sets are equal, we've got to go back the other way. So if we take something in the perp of the row space, all right, so X is just something in the perp of the row space now, and we want to show that it lives in the null space. So if it lives in the perp of the row space, it means X dot R is 0 for all elements of the row space. That's what it means to live in the perp of the row space. Right? That's what it means for X to live in the perp of the row space. It means this holds for all R in the row space. So in particular, what does it mean? What does it imply? It implies that X dot Ri is 0, right, for every actual row. But I already know what this is. X dot Ri was A times X, the ith entry. Right, so I'm basically just working backwards from what we did above. But now I know that the ith entry of AX is always 0. That tells me that AX is 0, the 0 vector. So what does that tell me? It tells me that X lives in the null space. So what we've done now is said that if X lives in the perp of the row space, it lives in the null space. And we know that if X lives in the null space, it lives in the perp of the row space. So we know both directions. Right? So if assuming X lives in the perp of the row space means X lives in the null space, that means everything in the perp of the row space belongs to the null space. So the perp of the row space is a subset of the null space. So we've got both directions. Null space belongs to perp of row space. Perp of row space belongs to null space. Therefore, they're the same set. Right? Two sets are equal if and only if they're both contained in each other. They're both subsets of each other. And that's what you mean by two sets being equal. Right? We sort of intuitively say two sets are equal if they've got all the same elements, but what does that really mean? It means they're both subsets of each other. That's a precise way of framing that. So there we have proved that the null space is the perp of the row space. Okay? So we know how to decompose the domain of any matrix transformation into the row space and its perp, or equivalently the null space and its perp. And we therefore know how to decompose the codomain into the column space and the cokernel. Okay, that's enough for today. So just as a